This is part 2 of integration by substitution. So if you have not watched the first video, part 1, go back and watch the first video because we went over all of these examples here. Went over many examples, and we got down to here to the basic guidelines for making a change of variables, which is u-substitution. That's what you're doing, is you're changing the variables so that you can then integrate. Otherwise, you can't integrate it. You're not able to. All right, so first of all, you have to choose what you're actually going to substitute in, or out, I should say. You have to figure out what is that function that I'm going to choose. And again, it's going to be the inside of your composite function. Okay, it's going to be the inside of your composite function. And then you go ahead and find the derivative of this thing right here. And you would get du over d. I always put du over dx here, but it's the same thing, du, because you multiply each side by dx to get this. And a lot of times you want to solve for dx. Sometimes you'll see that that is a perfect substitution for what's already in there because it works out nicely. Just kind of depends on what you need to do. Rewrite the integral in terms of u, so you're getting rid of all of the other variable, whether it was x or t or p or q, whatever the other variable was, you're getting rid of it entirely, and it's all going to be in terms of just u. If you go ahead and step 4 is you integrate it, then plug back in the g of x that you originally substituted u for, and then you can check your answer by differentiating, because if you differentiate, you should get the original function that you started with. So those are just a quick rundown of kind of the steps of how to use u-substitution. We've been using them in several of the examples. And the general power rule is something very similar to what we've done, but it's just kind of a shortcut. I'm not a big fan of just using shortcuts, but understanding them well enough that you can develop the shortcut on your own. And so, for example, down here, I'll go over one of these and what I mean. You have this function, it's composite function, where this part right here, the 3x minus 1, that's the inside. And if you think about u-substitution, you're going to end up dividing by the derivative of that, right? That's because if you do this enough, you'll see that, okay, my u is the 3x minus 1. My du over dx is equal to just 3. And when I solve just for dx, okay, when I solve just for dx, or even if I solve for du, du is equal to 3 dx. Look at this. Look what happens. 3 times dx, 3 times dx. And I can just substitute, get rid of the 3 dx, and it becomes just 3. Oops, I substituted u in for that. U to the 4th, dx times 3 is the same thing as du. Okay, so you ended up dividing by the 3, which got rid of that anyway. And that's basically what this shortcut up here, the general power rule, is explaining. Function like this, the g of x, that is your inside parts, and you notice that the outside part has the derivative of your inside part, just like down here. The outside was 3, the derivative of the inside was, the derivative of 3x minus 1 was 3. They're going to end up canceling anyway, and so the rest of this statement goes and kind of says that same thing. But again, it's a shortcut, which I'm never a fan of, just memorizing shortcuts, but understanding why or how the shortcuts work. This is what you end up doing, which is exactly what we did down here. If we were to finish this, this would be u to the 5th over 5 plus c, and you just plug the 3x minus 1 back in there. Right, there's our answer, and you can see in the general power rule, that's what we ended up doing. We added 1 to the exponent, divided by that new exponent, because we noticed that the derivative of the inside is exactly the same thing as that number or that function, whatever is value, whatever it is being multiplied to it. Okay, Now, again, using a shortcut, I wouldn't focus on how to use the shortcut, but then understanding what u-substitution is doing. Go ahead and solve B, C, and D. And look for the patterns. Look for the patterns as you're doing them. So pause the video, try those, and then come back. First one, you notice right here, my u is x squared plus x, because the derivative of x squared plus x is 2x minus 1, or sorry, 2x plus 1, which is going to simplify nicely with that, but I went ahead and kind of showed you why that works, because du over dx is the derivative of the function u with respect to the variable x. That's what this stands for, is 2x plus 1, and when you go through and solve for dx, get dx by itself, you get du over 2x plus 1. So we're taking this and we're going to substitute it directly in there for dx right there, which is what we did right there. And voila, you notice right there, that's where those end up canceling out. And then you have just the integral of u du. Those variables are the same. We can integrate it. You get u squared over 2. And then right here is where we substitute back in the x squared plus x in for u. And so you get x squared plus x quantity squared over 2, and then the plus c. And we're going to do a couple here in a little bit where you don't have to have the plus c because you actually have the limits of integration. Again, I'm not a big fan of shortcuts because they work like 1% of the time. But if you just work this one out, you see you have your u substitution, and then it ends up canceling when you substitute in for dx, du over negative 4x. So that's where the negative 4x's end up canceling out rather nicely right there. And you have just the integral of u to the negative second, which when you add 1, that gives you negative 1 divided by negative 1. And you get u to the negative 1 divided by negative 1, which is the same thing as negative 1 over u. And substitute that back in, and we have that function right there as our integral. Let's take a look at d. On d, we start off, the u is that inside part. Remember, cosine squared, that's the cosine of x quantity squared, so that's your inside part. When you find the derivative of that, you get negative sine, and then you substitute in du over negative sine of x in there for dx right here. And you notice the negative sign, or actually the signs will cancel, but you still have that negative out front. It's very important that you don't lose that. And then you would have the integral of negative integral of u squared du, which is u to the third over 3, and you have that negative out there. And then when you substitute it back in, it's negative cosine x quantity to the third over 3 plus c. A couple examples of where you're changing the variables of definite integrals, and that's where you have the limits. When you do that, you'll have to then, there's two ways you could do this. You could substitute that back in like what we have been doing, right? So you'd plug whatever you substituted u in for, or you could plug your limits into what you substituted u in for and use those as your new limits. So there's two different ways you could go about problems like this. So let's try one down here. For this first one, go ahead and use u-substitution, go as far as you can, and then come back to the video to see where you're at. Okay, but this first one, we're going to keep the limits and changing back into terms of x, and the other one, we're going to change the limits. Here, at this point, is where you could either go one way or the other way. Okay, so the first thing we're going to do is what we've been doing is substituting this, the x squared plus 1, back in for your u. And then don't forget your limits of integration, because we still have this from 0 to 1. And when we substitute that back in, you would end up with 1/8 times x squared plus 1 to the 4th. And that is from 0 to 1. So when you plug in your upper minus your lower, when you plug in your upper, you get 1 squared plus 1 to the 4th minus your lower, 0 squared plus 1 to the 4th. That is 16 minus 1, which is 15. And so our final value for that integral is 15/8. Now, let's go ahead and do the same thing, keeping it in terms of u, and actually, again, understanding what we're doing versus just memorizing shortcuts is really important because it is at this point right here where the change occurs. And so that's where we're going to pick it up. So you would have u to the fourth over 8. And again, that is from 0 to 1. However, remember these here, both of these are in terms of x. And we need them in terms of u. And so in order to get them in terms of u, we're going to plug 1 and 0 in here. So you would have u is equal to 1 squared plus 1, which is 2. And then u is equal to 0 squared plus 1, which is 1. Then we're going to then change the limits of integration, which were in terms of x. Now when we plug them into the function of u, they become, your lower limit is 1 and your upper limit is 2, because when we plug 0 in, we got 1. We plugged 1 in for u, or for x, to find what it is in terms of u. That's how we got 2. Now you plug these limits in. So you would have 2 to the fourth over 8 minus 1 to the fourth over 8. That gives you 16 eighths minus 1 eighth, which is 15 eighths. Okay, so we get the exact same thing, but instead of plugging the function back in, so here's where we went different. Instead of plugging the function back in, your limits remain the same. We plugged our limits in to figure out what is 0 and 1 in terms of u, because 0 and 1 are in terms of x, and we use those new limits and keep it as a function of u. Go ahead and try this one. Pause the video, come back, and see how you did. This is the last one, so I really don't care how you do this. Just get her done. You can either plug the function back in or change the limits, either one. Okay, so this one is rather involved once you really get into it, because there's the two different kinds of substitutions. You know, you have the u-substitution, that is the 2x minus 1. I think there's even a way to do this when you have u is equal to the square root of 2x minus 1, but I just made it 2x minus 1 because the derivative of that is 2, and you notice that doesn't cancel out with that x. When you substitute the du over 2 in there for the dx, that's why you have to then substitute in what was u originally, and that was the 2x plus 2x minus 1, and then solve for x, and you would get u plus 1 over 2. Okay, and then that is where we're going to substitute the u plus 1 over 2 in there. The over 2 I brought out. Here's the u plus 1. So you plug it in there for x. It's over the square root of u, but then simplifying this, u plus 1 times u to the negative 1/2, which is the same as 1 over the square root of u here. Right? When I multiply this in, you would get u to the 1/2 plus u to the negative 1/2, distributing that in, so that's what we have here. And then at that point, we can integrate. You add 1 to the exponents, and then divide by that new exponent, or multiply by the reciprocal, which is what I did. And that gets us to this point, but we have to now change our limits, because I want to keep it in terms of u. So I'm going to plug in 5 and 1 into x here. And you end up getting your upper limit as 9 and your lower limit as 1. So you plug in your upper minus what you get when you plug in your lower, and that's what starts here. And from there, it's just simplify, 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 simplify. Algebra is, calculus is algebra on steroids. It's a lot of simplifying. Keep fractions as fractions. It's a lot easier. But you should simplify it all the way down to 10 and 2/3 once you're all done with this problem. And that is the end of our notes. We did lots of examples because the most difficult part about u-substitution is there's so many different varieties, but again, understanding the process versus trying to memorize it is super important, because we can throw something at you that's just a little bit different. If you don't understand what's going on and you try to memorize it and fit into a memorized pattern, it's not going to work out for you.